When the solar system was forming, a massive cloud of primordial gas and dust swirled around a young Jupiter. From this exact same mixture of material, 4 giant moons were born: Io, Europa, Ganymede, and Callisto. 3 of these worlds followed the standard path of planetary evolution. Io became a volcanic world that constantly repaves itself in molten sulfur. Europa developed a churning interior beneath a fractured ice shell, and Ganymede built a layered metallic core capable of generating its own magnetic field. Then there is Callisto, a dark, sooty ball of ice and rock sitting on the outer edge of the system that simply stopped evolving. It holds the oldest, most heavily cratered surface in the solar system. Every asteroid strike from the last 4 billion years is still visible, tightly packed and overlapping, because Callisto lacks the geological activity needed to erase them. On paper, a world this size should have generated enough internal heat to shift its crust and rebuild its surface. Understanding why it remained geologically inert requires looking at the specific mechanics of how it was built and where it ended up. Look at a typical planetary cross-section. When a young world forms, the heat of its creation melts the interior in a process called differentiation. Gravity pulls heavy metals down to form a dense core, while lighter rock and ice form the crust. But data reveals Callisto never separated. Beneath its ice shell, the interior is a chaotic slurry of rock and ice, blended like frozen mayonnaise to its center. Building a planetary moon out of violently colliding space rocks generates an absolutely enormous amount of kinetic heat. Preventing that heat from accumulating enough to trigger a global meltdown depends entirely on the timing of the accretion process. Callisto formed through a process called pebble accretion. Instead of being violently hammered by large asteroids, it was built by a gentle drift of tiny icy pebbles over 2 million years. This slow pace allowed the heat of each impact to radiate into space before the next layer settled. Because its interior never reached the temperature threshold for a global meltdown, Callisto was essentially locked in mid-development, a planetary embryo that never completed its birth. Here is the orbital path of Jupiter's inner moons. They are locked in a precise rhythm called the Laplace resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. As they line up, they exert a continuous gravitational tug on each other, generating massive internal friction and tidal heat. Callisto orbits completely outside of this resonance chain. It sits far enough away that it receives absolutely zero tidal heating from Jupiter. This isolation was caused by a pressure bump in Jupiter's primordial gas disk. This ring of dense gas halted Callisto's inward migration during the solar system's infancy, permanently stranding it on the outskirts. This orbital exile starved Callisto of the friction required to power modern geology, dooming it to remain a cold, stagnant world. Callisto's stagnant surface is occasionally interrupted by unique geological formations. Its largest impact basin, Valhalla, doesn't look like a standard deep crater. It features massive, concentric bright rings stretching out 1,900 kilometers. These rings are frozen ripples, created when an asteroid punctured the crust and splashed into a warm, slushy liquid layer beneath. The circular shockwaves were locked in place almost instantly by the freezing vacuum of space. The existence of this liquid layer was confirmed by NASA's Galileo spacecraft. Its instruments detected an induced magnetic field wrapping around the moon as it orbited Jupiter, the signature of a highly conductive saltwater ocean. For decades, skeptics argued this was an atmospheric illusion. They suggested that Callisto's electrically charged ionosphere was conducting the currents and mimicking the magnetic signature of an ocean. A 2024 statistical analysis from the Jet Propulsion Laboratory settled the debate. The induced field is too strong to be produced by the atmosphere alone. The data requires both an ionosphere and a massive subsurface ocean sitting 100 to 250 kilometers deep. This ocean survives through a cryogenic thermos effect. Callisto's dead, 200-kilometer-thick ice shell is such a perfect insulator that it traps trace amounts of radioactive heat and ammonia antifreeze, keeping the hidden ocean liquid precisely because the surface is so inactive. On Earth, the deep ocean supports life because the water directly contacts a hot, rocky seabed. This direct contact creates hydrothermal vents, powerful chemical engines that spew mineral-rich nutrients and thermal energy into the water. This chart of Callisto's interior shows a different environment. Beneath the top ice, the heavy water column compresses into dense, exotic crystalline phases, known as Ice V and Ice 6. This creates an impenetrable ice floor that separates the ocean from Callisto's rocky interior. Without direct contact with rock, hydrothermal vents cannot form. There is no mineral flow and no volcanic heat, leaving the water completely devoid of nutrients. Callisto holds more liquid water than Earth, but this planetary confinement makes it a pitch-black, sterile desert, incapable of supporting life as we understand it. While the interior is locked away, the surface is slowly disappearing. Exposed to the vacuum of space, dirty ice sublimates, turning directly into gas. This erosion leaves behind a heavy blanket of dark organic soot and 100-foot-tall spires of pure ice pointing into the void. Callisto's failure to evolve is actually a success of cosmic preservation. By remaining stagnant for 4 billion years, it has perfectly archived the primordial ingredients of the early solar system. In the 2030s, the European Space Agency's JWST mission will arrive to scan this archive with advanced radar, looking directly through the ice of the world that time forgot. If you found this journey into planetary stasis fascinating, hit the subscribe button and let us know in the comments. Do you think the JWST mission will uncover any final secrets hiding in the solar system's oldest archive?